Let's revisit example 1, in which we integrated the function f of x, y, z equals e to the z over the solid E that's given by the plane 3x plus 2y plus z equals 6 and is bounded on the sides and below by the coordinate planes x, y, z equal to 0 respectively. So we said this was a type 1 region, and it is. It's bounded above in the z direction by this plane and below by z equals 0. But I can also think about it as a type 2 region, and that's what we want to do in this example. So in this case, in terms of the y direction, so at this axis right here, we can see it's bounded below by y equals 0. And it's bounded above, again, by this plane, which I can think of as y as a function of x and z. So what function is that? Well, if I solve for y in the equation 3x plus 2y plus z equals 6, I get 6 minus 3x minus z all divided by 2. Alright, so that's the upper bound surface in the y direction. Okay, so then we think about the projection down into the xz plane, and that's actually this purple shaded region right here. And we can think of the z bounds as being functions of x, and then the x bounds as constants. So this is a triangle, and what triangle is it? So if we're in the xz plane here, well, I just set y equal to 0. I get 3x plus z. 3x plus z is less than or equal to 6. So the boundary is 3x plus z equals 6. So in x equals 0, z equals 6, right there, and then when z equals 0, x equals 2. And so I get this triangle, and of course I have x equals 0 and z equals 0. Okay, so that's this triangular region that's shown right here. Okay, so I see I have x bounds from 0 to 2, and z bounds from 0 to, then I solve for z here, and I get 6 minus 3x. Okay, so now I've written my region E in terms of my coordinate y being bounded by two functions of x and z, my coordinate z bounded below and above by functions of x, and my coordinate x bounded above and below by constants. So at this point, I'm ready to set up my triple integral E as an iterated integral. So it's going to be from 0 to 2, from 0 to 6 minus 3x, and from 0 to 6 minus 3x minus z over 2. Alright, now we have our integrand e to the z. That doesn't change. And now this time, because we've set up our integral in terms of y first, we're integrating dy and then dz and then dx. Okay, so this is a type 2 iterated integral because we're starting with y. Okay, so now we get into the single variable calculus. And the first thing we have to do is integrate this function with respect to y. Now it's constant with respect to y, so I just get y e to the z evaluated from 0 to 6 minus 3x minus z over 2. I still have my integrals with respect to z and x left. Alright, so we plug this in, and what do we get? So we simply get this term, or this factor right here. So we get 6 minus 3x minus z over 2 times e to the z dz dx. Alright, so now our next iteration with respect to z, and there's really a couple different integrals here. There's the term with 6 minus 3x, which is constant with respect to z, and then there's a term with a z in it. So we really should handle each one of these separately. The 6 minus 3x term gives us 6 minus 3x times e to the z over 2. That's the antiderivative. And then we have minus, and then the antiderivative of z e to the z over 2, which is z minus 1 e to the z over 2. Now both of these are evaluated from z equals 0 to z equals 6 minus 3x. And then I still have my integral with respect to x. Okay. At this point, I'm going to pull a fast one here and just show you what this function is when I evaluate z equals 6 minus 3x and z equals 0 and simplify it without explicitly writing out the work. So I get an e to the 6 minus 3x over 2, and then I get a 3x minus 7 over 2. And what happened here is I plugged in z equals 6 minus 3x and z equals 0, subtracted, and then there's a fair amount of cancellation happening, and it simplifies to this function. Alright, so now we have our third iteration, and now we're integrating with respect to x. And so we get e to the 6 minus 3x divided by negative 3, so I end up with negative 6 evaluated from 0 to 2. And then I have plus 3x squared over 4, and then minus 7x over 2 evaluated from 0 to 2. So this first term gives me an e to the 6th minus 1 over 6, and this term gives me, when I plug in x equals 2, I get 4 over 4 here, so I just get plus 3, and then when I plug in 0, I get 0, and then here I get minus 7 halves times 2 is minus 7. And in the end, I end up with e to the 6th minus 1 over 6, and then this becomes a minus 4. And that checks out. That's exactly what we got in example 1, even though we set it up as a type 1 integral. And that's what we should expect. If a region or a solid in R3 is both type 1 and type 2, then either way we set up the integral, if we're able to carry through the calculation, our answer for what the triple integral over e of f dv should be the same. Because in the end it represents the same really geometric quantity, or the same integral. So it's just a matter of how you get there. In example 1 we used the type 1 iterated integral, and now we use the type 2, and we've seen that we get the same answer in either case. So you always have both options available, and as far as choosing between them, it's a matter of what you're comfortable with, and sometimes you can see that the work was slightly different. So in one case it might be simpler to choose one over the other, and that usually has something to do with looking at the function and looking at the bounds, and sort of as a matter of experience taking your best guess at which type is most advantageous to you. But the choice is really just a matter of convenience as you're doing the work, and as we saw here, it's not going to give you any new mathematics. The mathematics will work out the same, so it's whichever option is best as far as getting the work done.